due to the full course that we're going to be having in quite a lot of different time frames and geographical locations. So, as you can see also from this slide, this is going to be a 5-day course that covers fundamentals and workshop related to waste heat recovery systems. I mentioned here some of the different upcoming courses that we're going to have. This is just to give you an idea of some of the different courses that we offer. This doesn't include everything that we do. It's just to give you a flavor of this. All right, so thank you very much for your patience, and I'll be getting started with the webinar now. So here is the agenda that we're going to be covering today. So I'm not going to introduce the company. If you want information on this, just feel free to reach out to us, and then we can cover this into greater details, including information about how we can help you as a consulting company, a training company, or a software company, which are the 3 things that Softinware does. All right, so this webinar is going to be divided into 4 parts plus a conclusion. The first part is going to be an overview of the full class contents. So what I'm going to be doing is introducing some of the different sections and chapters that we're going to see inside the course, what the course entails, and so on, just to give you a flavor about the extent of material that is covered in this particular training. The second part is going to be an introduction to waste heat recovery. This is going to be to allow you to get some background information about what I'm going to be discussing in the third part, which is going to be devoted to recovering the waste heat, so waste heat recovery. In the last part before the conclusion, we'll talk a bit about Turbomachinery design process, and I'll show you an example of exercise that can be done during this particular full training. So this is going to be acting as a live part of this webinar. And then, as I mentioned, I'll be finishing with some conclusions. All right, so let's move on with the first part, which is going to be, again, an overview of the full class content. First of all, let me introduce some of the different reasons why you may want to attend this course. As you'll be able to see, it's going to be very extensive, very comprehensive course. I mentioned it's going to be 5 days times 8 hours per day, and that keeps the trainees and the instructors pretty busy for the entire week. What we're going to be covering, again in the full course, not in this preview, is going to be ranging from fundamentals to some of the more advanced topics, which are going to be related to waste heat recovery systems. And for some of the different topics, we're going to be seeing also quite a number of exercises that can be hand exercises or using software as well. So we'll be looking at cycles, and we'll be looking at the design of turbines, both axial and radial, within the AxSTREAM and AxSTREAM software. And of course, there's going to be different demonstrations in the full course of some of the different case studies that can be done related to this topic of waste heat recovery. Finally, we limit the number of people that can attend. This allows us to maximize the individual attention. So we do have a few spots left for our next courses in Boston. I forgot the date, but it was on the first slide, and it's going to be on the last one as well. So if you do want to attend, please feel free to reach out to us before the spots are taken. The aim of this course is going to be to provide engineers with a better understanding of what waste heat recovery is, as well as to give them some knowledge and the tools that are going to help them determine the viability, design, and performance of a WHR system and the different components that it's going to include. So this course is going to be targeted toward quite a lot of different demographics, I would say. So in terms of engineers, engineering managers, and engineering students as well. So whether you're looking at expanding your portfolio of skills and knowledge, or you want to deepen your understanding of what waste heat recovery is, or if you just want to get an idea of what some of the different people that you manage are doing. All right, so the full course theoretical content is going to be divided into 10 different sections or chapters. So these are going to be the titles of each of these different chapters. So the first one is going to be an introduction to waste heat recovery. I'm going to go a bit deeper inside each of these in the next slides individually, so you'll get a better understanding of what each of these chapter includes. Second one is going to be the basics of gas dynamics, fluid properties, thermodynamic cycle. Then we talk about heat exchangers, turbines in detail, so the design, the analysis, the optimization, blade profiling, pumps, flow and speed control systems, and finally some of the different development and challenges that we are seeing in the industry about those. So I mentioned that these 10 chapters would be theoretical, and also mentioned that we're going to be doing some exercises and some software practice. So we can see here we're going to have some hand calculation, some in-software exercises, and we'll also take you through the entire design process of both axial and radial turbines in the topic of waste heat recovery. So as I mentioned, it's a pretty extensive course. So the first chapter deals with an introduction to waste heat recovery. So in it we see what is waste heat, what are some of the different sources that we're going to be seeing for this, how to assess these sources and understand the different opportunities that we're going to get for each different instance. We're going to be seeing also the current technologies and systems that are used for waste heat recovery. And finally, we move on to an economic evaluation of WHR systems. For the next few slides that relate to the overview of the full contents, everything that's been underlined are some of the topics that are going to be super briefly discussed in this preview. So don't expect it to be the full course in an hour. As I said, we're kind of shrinking a 40-hour course into a very, very short preview of an hour. The second chapter deals more with fluid properties, so both as gas dynamics, fluid properties, and cycle applications. So one of the big topics that we're going to be discussing is going to be the organic fluid selection, which is going to be one of the most crucial criterion regarding organic Rankine cycles. And in terms of cycles, we're going to see different kinds. So the Rankine for steam, the Brayton for gas, combined cycle, different configurations, supercritical CO2, which is very popular these days, and the organic Rankine cycles that I'll quickly introduce toward the half of this presentation. And finally, we see some of the different applications of ORC systems as well. I forgot to mention, if you have any questions, you can always type them in the chat box, and I'll be answering them at the end of this presentation. So don't hesitate to ask away. The third chapter is going to be related to heat exchangers. So we're going to first give an introduction to what heat transfer actually is. We give some information regarding some fundamental knowledge of heat transfer, just to give a basic background so students understand what is going to be covered in this particular chapter. We classify the different heat exchangers that exist, and then we go into some details about what are the different designs that we're going to be seeing for this particular component that's very important in a waste heat recovery system. And finally, we give some information about how we can select between different types of heat exchangers. So I mentioned this course was very focused on turbines, although this is not everything that we cover. But this chapter, the fourth one, is going to be the first chapter that we start to really talk into details about turbines. So first thing that we do is introduce what a turbine actually is, which is something I'm going to be presenting toward the end of the presentation. We look at the overall turbomachinery design process, some of the different factors that are going to be affecting the turbine operation, the different components that are going to be found in a turbine, both axial and radial. And finally, we're going to be seeing the losses and the loss models that are going to be present in both technologies. Why we look at losses is because this is going to give us some understanding about how we can improve the efficiency of our current machines, or as we are designing them. So while the fourth chapter was a bit more general, the fifth one is going to go into great details about the preliminary design or conceptual design of both axial and radial turbines. So first of all, we talk about what the task formulation is going to be. So what does it include when we say that we're going to do the preliminary design of a turbine? Then we look at the procedure for both types of machine, look at the volume design for the radial configuration, and finally we show you the full procedure in the AxSTREAM software. In the sixth chapter, we're going to be talking about turbine analysis and optimization. So once we've done the detailed design of preliminary design of the machine, we can move on to the detailed design and perform some analysis of this machine to obtain things like the performance, the distribution of the different flow coefficient and so on, as well as the losses. So we can do this for design and off-design conditions. And we can also perform some optimizations as well. So we talk about the optimization methods, principles, and processes in this chapter. Some of the different operating conditions that are not going to be at design point include the startup and the shutdown, which are also going to be introduced in this particular chapter. And for radial machines, we'll also talk about variable area nozzles, about how we can control the amount of flow that's going through a machine in order to be able to keep a good efficiency at different off-design conditions. Seventh chapter is going to be dedicated to blade design. So we first of all go a bit about a more basic theory about defining what the concept of boundary layer is, how does the flow behave in a blade channel. We talk about the different geometric properties of a profile and how to select them in order to create the optimal profile for a given set of boundary conditions. We discuss supersonic flows, which may or may not happen depending on the configuration of the machine and the boundary conditions. And then we move on to the full 3D blade design of both axial turbines and radial turbines. We finish this chapter with something a bit more general, which is going to be when to choose axial versus radial turbine configurations. This chapter is not going to go into as much detail, but we do discuss pumps, so we do an introduction to them, and we focus this chapter on introducing the different specificities of pumps given the context of ORC units. We mentioned the different types of pumps that are going to be available, and finally we also discuss some of the different factors that are going to help you figure out which pump you should be using for a particular application. The ninth chapter is going to be fairly short. We deal with flow and speed control systems, as I've mentioned, and the 10th one is going to be the last chapter here, and it's going to deal with developments and challenges in the waste heat recovery industry. All right, so that concludes the first part of this webinar. The second part, as I mentioned, is going to be dedicated to the introduction of what the concept of waste heat recovery is. So the title of this slide is pretty explicit. Energy is money, and that's going to be pretty much what is going to be the main guideline of waste heat recovery. So first, let's try to understand what waste heat actually is. So anytime we lose or we dump heat into the air or into the water, this is going to be energy that could be used to create more energy or to be used in any other aspect. So I'll be going into a bit more detail about this later on. So, however, even though it can be recovered in most instances, it's not always done. If you want to know more about why it's not always done in terms of feasibility, then you can come to the class and we go into pretty good details about this. What we can see on the chart here on the right is going to be a prediction about the cost of crude oil. So this is going to be for example, for the different fossil fuels that can be used, and as we've been taught for quite a number of years, the price of oil is predicted to increase significantly, which is why we're going to be looking at other ways to generate energy. And if we want to be able to reduce the cost of energy, we're also going to need one of the ways to decrease this cost is going to be to look at some optimization of the energy utilization, which is why we're looking at waste heat recovery. So waste heat is going to be any heat that's going to be rejected from a process at a temperature higher than the ambient conditions. So whether it's going to be dumped into air or water. For example, if you take some water from any process that's going to be rejected, for example, at 50 degrees Celsius into a lake that's going to be at 15 degrees Celsius, then here you have a temperature differential that could be used to many different applications. So this temperature that we are ejecting the heat at is going to be defined by what we call the quality of the waste heat. So this is going to be the quantity of useful energy that's going to be available and that's going to be contained in the waste heat source. So usually that's going to be the temperature. The higher the temperature, the more energy you can get. That's also going to be related to the mass flow rate as well. Waste heat can be in either gaseous or liquid form, so we're going to be talking about both very briefly here. As we'll be able to see in the next slide, the largest portions of waste heat we're going to be seeing are going to come from the power stations, vehicle engines, and industrial plants. So this is where the most efforts in terms of waste heat recovery are going to be concentrated. So the waste heat recovery concept is to capture and reuse the waste heat in different processes. So it can be used, as I'll mention later on, for heating, for generating mechanical energy, electrical energy, and so on. So we'll be able to see this in just a few slides. This is just a very brief slide that I'm not going to cover into too much detail, but this is on the left to show you some of the different industries that I was talking about for waste heat sources. We go into much more detail in the full course as well. Here on the right side, you can see a table of typical waste heat temperatures. So this is to give you an idea about the range of temperatures that we're going to be seeing. Here we can see the lowest temperature we're going to have in this table is going to be 27 degrees Celsius, and we're going to go up to 1650. So as you can imagine, whether you're dealing with 27 degrees Celsius or 1600, we're going to be looking at probably different types of technologies and probably different levels of efficiency as well, and ways to look at the problem in general. So again, this is mentioned into more detail in the full course. I already discussed the fact that there's going to be different options in order to recover the waste heat. So these are just some of the different options that are going to be available. So I'm not going to go into details here, but we can see that the energy can be recovered either on-site or off-site. For example, in the case of cogeneration, we can recycle the heat back into the process, for example, for fuel preheating, as an example. We can use it for heat pumps, or we can use it to generate electricity, which is going to be where we spend most of the focus in this particular preview, but we could discuss any of them as well. The third part relates to recovering the waste heat, now that we've defined what it was. So in order to do this, we first look at the different technologies and systems that are going to be available for waste heat recovery. So we discussed in the full course the water jacket heat recovery, exhaust stack, and the heat to energy technology. Here we're going to be focusing for this particular preview on the last option here, which is going to be used to convert waste heat to electric power. So this can be done through some different technologies that I'll be mentioning in the next few slides. But they're going to include the Rankine, organic Rankine cycles, Kalina cycles, exhaust gas turbines, also called the Blowdown turbines, and many more as well. This slide is again to kind of do a parallel with the waste heat sources that we saw in the table a few slides ago, where we had the different ranges of temperatures depending on the industry. Here this relates to the temperatures that we usually find in the different engineering cycles. I highlighted in yellow some of the different cycles that we do cover within the course. So you can see here on the left the gas turbine cycle, here in the middle the Rankine cycle for water/steam, Kalina cycle that we'll be discussing here as well, and the organic Rankine cycle as well. We can see here that we are going to be decreasing in temperatures, which is why we're going to be looking at ORC technologies when we cannot get enough energy to be able to recover steam to evaporate water into steam. So the first technology here is called the Blowdown turbine, also called Turbocompounding. So its goal is going to be to recover the energy from the exhaust of usually an engine, and this is done by simply putting a power turbine directly outside or at the exhaust downstream of a turbine. Sorry about that. So for example, here if we see a turbocharger, we have the engine, we're going to have the compressor, the turbine, and here the exhaust are going to go through this power turbine, which can then bring mechanical work back to the engine, or for example power a electric battery. Here this is about a simple Rankine cycle. I'm going to have 3 slides on the Rankine cycle, although I'm not going to go deeper into this. I just want to quickly mention the way that it's going to work. So here we can see the most basic elements are going to be these ones. Here we have a boiler that's going to be used to evaporate some water, liquid water coming here, into steam, so vapor, which is going to be here. This boiler uses the energy that can come from different sources, including waste heat sources. So here we're bringing some heat in order to evaporate our water. We pass it through a turbine, generate some mechanical energy, can go through a generator to convert this into electrical energy. Downstream of the turbine, we have the condenser, and then the pump over here. Here, to be able to relate this to the next slide, we can look at the efficiency, one of the typical efficiencies of such a cycle, which is around 30%. Here, this is also a Rankine cycle, but we're going to be adding a few components to it, which is going to be a reheat. And here we can see the thermal efficiency of the cycle was increased by quite a significant amount. So if you come to the full course, we actually explain why this happened and how it happens. And we're also going to details. We're also going to some examples that are going to be a bit more complicated, like for example this one right here, which is going to be a regenerative feed water heating steam cycle. On the same principle of the steam cycle, we have what we call the ORC, Organic Rankine Cycle. So here we can see we still have our heat source. Here this is going to be an evaporator, which is going to be very similar to the boiler that we just saw. Turbine, condenser, a pump, and a generator. So here we can see it's going to be similar technology, except that here the working fluid is not going to be water, but it's actually going to be an organic fluid. So an organic fluid is simply going to be a fluid that's going to be boiling at a temperature that's going to be much lower than steam. So we go into a very good amount of detail in the full course, including how to choose between steam and organic fluids, different working fluids depending on conditions, depending on environmental restrictions, and so on. And here, what we're going to be seeing that's going to be different from the Rankine cycle is that the hot resource, the heat source, is going to be, in this case, at a lower temperature. So this can actually come from any of these particular industries and some others. One of the ways to increase, or to possibly increase, the efficiency of an organic Rankine cycle is to look at transcritical and supercritical conditions for this particular cycle. So if you come to the full course, we talk about what a supercritical fluid is, how it can be advantageous in the waste heat recovery industry. On the other hand, we're going to see what are going to be some of the different additional concerns that are going to be addressed whenever you're going to be dealing with supercritical fluids, and a few more things as well. Here's one example of the cycles that we've created, and we published a paper on this, I think last year or 2 years ago. I mentioned that the organic fluid selection was one of the most important criteria when we're dealing with organic Rankine cycle. This is going to allow us to reach higher thermal efficiencies, so convert the energy in a better, more efficient manner. Depending on the applications, we're going to be using one fluid versus the other. It's not always going to be a matter of thermal efficiency, but as I mentioned, environmental constraints, availability, cost, and so on are going to also come into context. So here, simulating the cycle with a thermodynamic model and comparing the fluids in terms of cycle efficiency and output power, is going to be the best way to select a fluid for highest efficiency. Here I mentioned I would quickly introduce the concept of Kalina Cycle. So here it's going to be working around the same principle as the other cycle that we've seen so far, except that instead of having a fluid that was a pure fluid, water or an organic fluid, here we're going to be using a binary fluid, which is going to be a mixture of ammonia and water. In the full course, we're going to be discussing the advantages and disadvantages of the Kalina cycles compared to the single species working fluid systems. So now we move on to a completely different technology, which is going to be the Brayton cycle. So this is going to be used for gas turbine applications. So here we see a compressor, a combustion chamber, a turbine. We can see different configurations that are going to be available in the industry. These staying pretty simple. So obviously in this context, the Rankine and Brayton cycles are going to be very efficient, but they can both be used for waste heat recovery, power generation, and so on. So in the full course, we dive into details about the different specificities, advantages, and disadvantages of these different technologies, as well as some information about how you can better choose between one technology or the other. We'll also quickly discuss SCO2 cycles, so supercritical carbon dioxide, which is one of the working fluids that's been a lot talked about those days. So in this full course, we discuss the whys and the hows regarding the popularity of such technology. A lot of different applications, as you can see on the top of here. So far, we've only discussed one technology at a time, but there's also the opportunity to look at multiple configurations being used at the same time, so different combinations. In this case, for example, this is a waste heat recovery system for a large marine engine. So here we could see the efficiency of the system without and with the waste heat recovery system. In this case, as we'll see on the next slide as well, we're going to be using a Rankine cycle and a Blowdown turbine together. So here this allowed to recover up to 12% of the engine power. Here we can see the breakdown depending on the engine load about how much power is going to be generated by the power turbine here, the steam turbine, and the combined output of the two. So obviously if you use both technologies, the cost is going to go up, but you're also going to get, in certain cases, an increase in efficiency. So depending on what you're interested in terms of efficiency, cost, payback period, and so on, then you would use one technology or the other, or both. Here we have the idea of a combined cycle. So in this particular case, this is a configuration here and here where we have a gas turbine cycle that's going to be releasing some heat at a very high temperature, probably too high in this case. And this is going to be recuperated inside some what we call HRSGs, heat recovery steam generators, which are going to act just like the boiler that I introduced earlier. So here we're going to be boiling some water into steam, which is then going to be used inside a steam cycle over here. So now we're not only generating electricity based on the gas turbine cycle, but also on the steam turbine cycle. And that allows us to reach higher level of efficiency. This is, I would say, a very old number. Right now we're looking more at the 60%, even more 62% efficiency for combined cycle applications. This is the example of a gas and steam cycle, but we're going to have a lot of different possibilities. We can do gas and SCO2, we can do steam and ORC, and so on. So you can even go to multiple levels. Here I wanted to bring your attention to some of the typical efficiencies that we're going to be seeing for these different systems. I highlighted in blue the different systems that we do cover in the course. So solar, gas turbine, steam turbine, and combined steam and gas. There's going to be a few more that we do discuss, but we can see here the typical efficiencies. Let's This is just to give you a flavor of one of the many exercises that you can practice on during the full course. So in this particular exercise, we ask you to model this cycle, which is going to be a recuperated, we have the recuperator over here, a recuperated ORC system, given some boundary conditions. So first we ask you to model the cycle, run it, generate thermodynamic process, and then obtain the different performances. After this, we ask you to construct a map of dependency of, in this case, the thermal efficiency, shown here, versus the pump outlet pressure, and this is done for different heater outlet temperatures. So this is the graph that we're going to be seeing here at the bottom. The last part before the conclusion, that's the one that's going to include some live action, I would say, is going to be dedicated to Turbomachinery design process and the demonstration that I mentioned. So again, the demonstration is going to be one of the examples of exercises that you're going to be doing throughout the course. So first of all, let me define what turbine is. This is just going to be done in one sentence. It's going to be a device that's going to be used to convert the fluid kinetic energy to some mechanical energy. And this is done through an expansion process. So at the inlet of the turbine, here for the axial, here for the radial, in case with no volute, we're going to have a higher pressure than the outlet, here and here. So we're going to have an expansion process that's going to turn our rotors. I'm very much simplifying it currently. And this rotation of the rotor is going to be producing some mechanical work that can then be used to generate electricity. Yes, this is going to be the expansion process that we describe inside the course in details, and you actually get to do some hand calculation on this. If you have followed what I've talked about in the first part, we do cover the full design of both axial and radial turbine in this course. We do it at theory and hands-on practice with the software, from the 1D conceptual design to the full 3D design of the blades and the 3D analysis of the full machine as well. So both in terms of stress analysis and computational fluid dynamic calculations. Here, this is going to be two slides regarding the design process scheme. I have highlighted in green the different parts of the process that we can currently do with our own in-house tools. Everything that's going to be underlined is what is covered in the waste heat recovery course. Everything that's not underlined but still in green are going to be the different things that we're going to be covering in different courses. As I mentioned, we have this waste heat recovery course, but we also do quite a number of other courses as well. So here, if we look at the 0D level, we're going to be starting with some market research, come up with some different requirements. This is going to help us establish the initial data that's going to be used for the unit design, after which we can create the cycle and perform the design and off-design analysis of it. This is going to allow us to determine the boundary conditions for the pump or compressor, the turbine, and all the different auxiliary components that are going to be mentioned here. Some of them are mentioned here. So then, at this point, we move on to first the 1D level. So here, the pump, compressor, and the turbine are going to have a similar process. So I'm just going to focus on the turbine here. So we look at the 1D design and analysis. We look at the flow path detail design, the performance analysis at design and of design conditions. This can then be linked with the compressing component in a thermal fluid network software and or in cycle software as well. So here, this is where we have the double arrow in this case. That's going to allow us to run some iterations for the optimization of the components and the system as well. Once we finalized our geometry here, we can establish the 2D layout of flow path. And then we move on to the second slide, which is going to be the complete 2D layout of the entire unit. We move on to the 3D level with the design of the blade attachments. So that's going to include the wheels, the disc, the roots, the shroud, the lashing wires, anything you're going to have here that's going to be attached to the blade. We perform the 3D analysis in both FEA for structural and CFD for fluid dynamics. Then we look at the development of the bearings, the casing, the shaft, and so on, in order to be able to perform a rotor dynamics analysis. That's going to give us a final validation step for a particular design. Afterwards, we can go to the 3D subassembly, do the manufacturing drawings, and eventually come to the production and the after-sales market. In the course, we do give you quite a good amount of explanation, both axial turbine and radial turbine, as well as some exercises that are used to allow you to conclude on the feasibility of both technologies for particular application, and you're also going to be taken through the entire design process as well. This is one kind of going to introduce in the demonstration part, or the live software part, which is going to be coming up. So here I just want to introduce what I'm going to be doing in this case. So the design task that we consider in this case, again, is going to be taken from the course. In this particular instance, we're going to be working with an organic fluid, which is a refrigerant, the R245FA, which is pretty popular these days. We're going to be looking at these boundary conditions. So this is going to be the total inlet pressure, total inlet enthalpy, static outlet pressure, and here this is going to be the mass flow rate. So this is typically the type of thing that you're going to be getting from your cycle software, and then you're going to need to figure out the feasibility of the design of an axial turbine, a radial turbine, in order to select the most appropriate technology based on the performance and based on its size as well. And the focus here is made on determining the wheel diameter, or the hub diameter if you want, and tip diameter, the rotational speed, and finally the configuration, so axial versus radial. Alright, so let me move on to the software part, then I'll finish with some conclusions. I hope to be able to stay within the 1 hour time, and then I'll leave the floor open for questions. Alright, so the first thing that we deal with is going to be having to define our working fluid. So in AxSTREAM we have a specific tool that's going to be called the Fluid Designer. So here we are using the 3 properties from the RefProp NIST database, NIST RefProp database, in order to be able to create some fluid files that can be used inside AxSTREAM. So the reason why we do this is because, as you'll be able to see, we're going to have quite a big amount of different fluids that can be used. So both as pure fluids, predefined mixtures, or you can create your own mixtures as well. In this case, I just have one fluid, so I'm going to say simply this one. I can go to the setup menu, and I'm going to be creating the range for the particular fluid that I want to be using. So this is going to allow us to have a very accurate definition of the fluid properties for the range of pressure and enthalpy that I'm going to be using in my particular machine. So I've already selected my fluid. Now I need to select my my range of values for the enthalpy and the pressure. So this can all be taken from the cycle tool. Here I'm going to be using, so I know I have 517 at the inlet in terms of enthalpy. I'll give it a pretty big margin to be able to see a bit better the process. For the outlet, I'll put this at 400. Pressures, I'm going to be ranging from 3 instead of 3.6 to give it a small margin, and here I'll put it to 50 again to give us a bigger overview of the process. So here we can see the pH diagram. So here we're going to have the log 10 of the pressure, and here at the bottom, just covered by this. So we're going to be seeing the enthalpy value. Here in blue, this is going to be the liquid saturation curve, and in red, this is going to be the vapor line. So what we have at this point we're going to need to define for which exact range we're going to be wanting to use our fluid. Because here this is going to be for turbine, so we're most likely not going to be operating in this range, or we'll try to avoid this particular area as well. So based on my boundary conditions, I can create any shape of polygon that's going to be used to define my boundary conditions, or my range of applicability for this particular fluid. So here I'm kind of eyeing it like this. I'll be using a different fluid file afterwards, but I just want to show you the process. And here we define what is going to be the refinement in terms of fluid property calculation that we're going to have. So here, how many points we want to calculate in this direction, and on the saturation line. So here I'll just leave it to 20 and 20 to give you an idea of what it looks like. So here we have 20 in this direction, 20 points in this direction, which are all going to be represented as green points here. If, for example, I were to put 200 here, then we're going to be seeing that we're going to be getting 200 points in this direction, but still 20 in this direction here. So once we've done this, we can save this as an RLG file, which can then be used inside AxSTREAM directly. So this is what I'm going to be doing here. So AxSTREAM is going to be our software that we use for design, analysis, and optimization of turbomachinery. So we can deal with any of these particular machines. If we have some incompressible applications, we're going to also have hydraulic turbines and pumps as well, centrifugal, axial, single stage, multi-stage, which are available with a different type of license that is not portrayed in this case. So if you're wondering if we can do pump, the answer is yes. Here my focus is going to be on the turbine. We can see I have the choice between axial, radial, or mixed flow, which is going to be radial at first and then axial. I'll start with a radial turbine for now. Here I'm going to be doing a design from scratch. So I'll be selecting preliminary design, and here I'll be selecting the fluid I want to use for my calculation. So you'll be able to see in the software is going to be quite a lot of different fluids that are already embedded inside the software. But given the tool that I've shown you, which is one of the tools that we use to create fluid files, we're going to have the option to have way more fluids than what is currently available. So I know, for example, the fluid I want to use is going to be this one, so it corresponds to R245FA. We can see I have quite a few of these, and that's because they are going to have different density of points and different ranges of application for pressure and enthalpy. So I can click OK. It selects my fluid. I can refine the loss models, for example, and then I click OK to be able to start my preliminary design process. In here, I'll be specifying or inputting the module design settings, which are going to be, in this case, information about how I want to design my my radial turbine. So if I want to design for inlet rotor angle to be incidence or the middle angle, if I want a vaned or a vaneless nozzle, and if I want to have volute or no volute, with different type of volutes here. At the bottom here, I'll be inputting the boundary conditions, geometric parameters, and some geometric constraints as well. So here I want to make sure I don't run too much over for time, so I'll be opening a file. So this file is still going to be empty, except I'm going to have some values here that are going to be available. This way I don't have to type anything. That's not the most important thing to be doing. And as I'm going to be running this, I explain to you what I'm doing. So here I mentioned the type of data that I'm specifying, and here you can see that this the inputs are specified at both minimum values and maximum values. So this allows me to fix any particular value I'm interested in keeping constant. For example, here I know my inlet torque pressure is going to be 25 bars, so I put the min and the max to be the same. And here for the geometric parameters, if one of the things I don't know, for example, is going to be the stator outlet mean diameter, I can put at the range in order to determine what is going to be the best value that's going to give me a machine that's going to be acceptable and that's going to have a pretty good efficiency. So here what I did was to generate 250 different radial turbine geometries, out of which 88 actually fit the constraints that are specified at the bottom of here. So here, this means that on the 3D plot right here, we have 88 different points. Each of these points is going to correspond to a completely different radial turbine geometry. So In order to not have to click on each point manually to see which one we like and which one we don't like, we have a tool that's called the Design Space Explorer, in which we're going to have quite a number of properties that can be used to display on any of these axes for the graph here. For example, here I can look at efficiency on the z-axis, and as the color here as a function of the maximum Mach number. So here we can see, for example, that the highest efficiency is going to be in this range of Mach number here. So if I were to design a machine that's going to have a Mach number of, for example, 0.3, I'm most likely not going to be able to get as much efficiency as if the Mach number was around 0.6, for example. And here we would be able to see that as I'm going to be increasing Mach number to supersonic flows, I'm going to be losing some efficiency due to the shock losses. So here, if we were to continue running some more points, we will be able to see that this is going to drop over here as well. In the same way, we can look, for example, at, let's see, the rotor hub outlet diameter, and let's see the stator outlet mean diameter here. So here this is going to give us different kind of aspect ratios for a turbine. So here we can see this is one of the geometries that was modeled. I can see already that this hub diameter is going to be pretty small. We can see here indeed the value for this particular point, which corresponds to this geometry, is going to be small. We're going to be at around probably like 12 millimeters, which I can probably give you the exact value here. Yeah, that's it, 11.77 millimeters. So it's going to be way too small for such a geometry. So I'm going to be looking at increasing this. For example, I could select this point and see what that's going to give me. And I can see that this is going to be something that's going to be much more reasonable in terms of 2D shape. So here I have efficiency ranging from 68% to 94% in this case. So for example, if I wanted to get rid of any machine that's going to have an efficiency lower than 90% as an example, I could do so in this case, specify 0.9. And here we can see that it's going to get rid of some of the different geometries that are not going to be fitting the different filter that I specified. So this allows us to really tailor down what we want the machine to look like based on the size, based on manufacturability, based on the performances, flow conditions, and so on. So here, so far, I have generated a radial turbine with an inlet volute and an impeller. Now I can also look at some of the different configurations. So for example, I'll get rid of this. And instead of a volute, I'll have a nozzle. So here you can see I can very quickly change the, oops, what did I miss here? I can very quickly change the configuration. And let's see, what did I do? It's been working so far. What have I missed? That's slightly embarrassing. Sorry about this. Let's try this and see if it takes us anywhere. No, alright. Alright, I'm very sorry about this. I have 9 minutes left, so it's going to be a bit tough for me to be able to figure out what's going on. Just give me a brief second. Yeah, I'm not sure what's going on there. I'm very sorry about this. It's been working every single time I've been practicing on this. All right. Well, I'll mention that you can indeed do some configuration without a net volute, but with an inlet nozzle. I'll have to save this file so I can figure out what's wrong with it. But let me open a file that's going to be similar to what I wanted to show you. For example, this one. So in this case, for example, we would have a geometry that would be looking somehow like this. In this case, we have no net volute, and we have a vane at the nozzle type here. Here, one thing that we could do from here would be, let's see, okay, I have 7 minutes left. We could look at different, let's see. We could look at different rotational speeds. So instead of 25,000, I could bring it down to 1,500, and then see how that's going to be affecting the performance of the machine that can design here. So this does take just a bit more time. If it takes too long, I will stop it, because I do want to be able to show in a few minutes how we can design axial turbines. The process itself is going to be the same. Of course, we're going to be using a completely different solver and algorithm in the background, different loss models, and the parameters that we're going to be inputting are also going to be different. So here in this case, to save time, I'm only generating 100 different designs that are going to be similar to this one, but for a lower rotational speed. So here we can see I've now generated my 100 design. I can go back to this, and for example, for the rotational speed, I can put the color. Here, let's see, let's put the stator outlet mean diameter as X, that's good, the efficiency as D. In this case, we can see in red, this is going to be all the different solutions that were generated at 25,000 RPM, and in blue, the 15,000 RPM. So here we can see that for this particular rotational speed, the blue one, I'm increasing the efficiency on this axis as I'm increasing the wheel diameter, which is going to be on the vertical axis here. So in this case, I could, for example, increase the range of maximum stator outlet diameter that I'm going to be using in order to reach higher level of efficiency over here. I'm going to be doing this just very quickly, and then I'll move on to the axial turbine design. So here we can see indeed what I was talking about. So here we're populating with more points, and we can see again that as I'm increasing the wheel diameter, I'm going to be increasing the efficiency in this case. So here we're going to reach maximum around 220 millimeters, and then we can see this is then going to drop. So for a particular rotational speed, we're going to have a particular wheel diameter that's going to be optimum. So we do go inside the theory of this in the course as well. All right. So based on this, you can figure out if it's going to be a configuration that's going to be acceptable, if it's going to be a rotational speed that's going to be acceptable based on your bearings and so on. So this is really a very powerful tool. I have 4 minutes to show the axial turbine, so I'll try not to waste too much time. So here I'm going to be opening a project for axial turbine. So let's see. I'm going to be running it here. I'll be talking through it as well. So here, this one's actually going to calculate pretty quickly. We can see the boundary conditions are going to be the same one. Here, instead of specifying one value of rotational speed, I'm specifying it as a range, and I also have a pretty big range for the hub diameter, between 50 and 100 millimeters. Here, I restricted the number of stages to 4, but I could restrict it even more if I wanted to. We can see the geometry that's currently been selected by the software as being the one with the highest efficiency level. So we can see in this case it's going to be a 4-stage axial turbine. I could go in my Design Space Explorer and, for example, study what is going to be the influence of the number of stages on the efficiency that I'm able to get. So we can see for 1 stage, I can go up to around 76% efficiency, 2-stage, 82, 3-stage, 82.5, and 4 stages, I'll be around 86% efficiency, total to total in this case. So based on this, I could figure out and make decisions very quickly about the number of stages that would be preferable for me to use based on the size, based on the performance, and so on. Because as I'm going to be increasing the number of stages, chances are my costs are going to go up. So is it worth it to get, for example, 0.1% efficiency, but have an extra stage? So depending on which industry you're going to be working in, depending on different constraints, then you may want to use one versus the other. Here, one thing I do want to mention: if I restrict this to only subsonic flows, we can see all of the 1 and 2 stage configurations are going to go away. So now I'm left with at least 3 stages, which is most likely going to be more expensive than doing a radial configuration, as we saw earlier. And we also see that the efficiency is going to be lower than for the radial turbine as well. So here, based on this, I would be able to wisely suggest doing a radial turbine configuration in this case. Lower cost, probably lower size as well, and higher efficiency. All right, so I do have 2 minutes to finish with a conclusion, so let me go ahead and do this, and then I'll leave the floor open for questions. All right, the conclusions are going to be pretty brief. So we introduced the contents of the full waste heat recovery course. So we looked at the different chapters, what's going to be covered inside each of these, and we also went into a bit more depth for some of these different topics. So we define what waste heat actually is, where it comes from, some of the different ways to recover it. We looked at different thermodynamic cycles, including the Rankine cycles, Brayton cycles, organic Rankine cycles, and supercritical CO2 cycles for waste heat recovery applications. We discussed and presented what a turbine is and what its design process involves, and finally I demonstrated how you can use the AxSTREAM platform to design, in this case, a waste heat recovery system turbine, which in our case was best as a radial turbine. So it is just 11 o'clock here in Boston, so this is going to be the end of my presentation. Thank you very much for your attention. I'll be muting myself until some questions come up. If you do not have any questions, well, thank you very much for attending. If you do have questions, of course, thank you very much for attending as well. I look forward to answering your questions. All right, I see that the question for one person I do know quite well. The question is, how important / useful is it to have the fluids database for waste heat recovery modeling and design? So please correct me if I'm wrong, but I believe you are talking about the NIST database that we use under the fluid designer inside AxSTREAM. So, okay, thank you for confirming. All right, so this is going to be used, first of all, to define what fluid we want. In AxSTREAM, we're going to have the choice between different fluids that are already going to be embedded in your version of the software. But this list of fluid embedded inside the commercial tool does not include all of the different fluids that AxSTREAM can work with. So, for example, if you're working with particular refrigerants, or if you're going to be working with a particular mixture, we just don't want to include absolutely everything, because your mixtures can be changing. You can have some humidity in your fluid, so we really give you the flexibility to define anything that you want. So that was the first thing, flexibility of the fluid. The second part of my answer would be related to the fact that you actually get to accurately calculate the fluid properties for any range of pressure and enthalpy values that you're interested in for your particular machine. So, like in my case here, if you have a particular set of boundary conditions from your cycle, then you can figure out what is going to be the range of pressure and enthalpy that should be used for your turbine, I'm assuming in your case. So this is going to really allow you to have some very accurate modeling of the physical properties, which is then going to increase the accuracy of all the different calculations that you're going to be running inside AxSTREAM in this case. Hope that answers your question. If not, you can always shoot me an email or call me. All right, here I have a different question. Does the database have any combustion models or combustion gases, fluids? So yes. So I mentioned that the fluid designer that I presented is one of the tools that we use to generate fluids. The reason why I said one of the tools is because we have another one that's actually dedicated purely to combustion products. So in this one, you would specify exactly what fuel you're going to be using. So in terms of carbon atoms, oxygen, and hydrogen, or you could say, okay, I have this much methane, ethane, propane, and so on. And that's going to allow you to generate a different fluid file that you can use also inside AxSTREAM. And based on this, you can also specify within the software which value of air excess factor you want to use for your, in this case, I'm assuming turbine. So as, for example, you're going to be using cooling in a turbine, the amount of air that's going to be at the inlet of the turbine versus any of the stages is going to be different, and there versus the burnt combustion product, and therefore your fluid properties are going to be different at any streamwise point of the machine, as well as different spine-wise locations. So here we're actually able to recalculate the fluid properties at streamwise and spine-wise position for your machine. All right, it seems that it's all the questions that we have for now. I'll be staying online for just a few more minutes in case you can think of anything else you want to ask us. Otherwise, you can email us at info@softingware.com. I do receive these emails, so I'll be able to address it or pass it on to somebody else that would help you better than me. So I'll be, as I mentioned, I'll be standing by. If you have questions, feel free to do so. I do wish everybody a very good day, and thank you very much for your attention today.